Okay, we're going to learn how to create our own solar generator. And I like to say this is like a standalone solar system in a box. The purpose of it, solar generators are helpful if we're going to, you want a remote power source, such as when you're camping, or if you've got a remote location like a chicken coop or something like that where you want to have some light, or just emergency backup power when the power goes out. These solar generators can be as large as what you need to power your whole house. Of course, what would be the point? You may as well have a standalone solar system at that point. Or a small little guy like this in the box. This generator that we're talking about right here is enough to run a small home office for about 6 to 8 hours, depending on what you plug into it. A standalone solar system has 4 main components that we need to be looking at. The first is a solar panel, and this solar panel, this particular one is what's known as a polycrystalline silicon-based solar panel. You'll also run into monocrystalline. The only difference between the two, as far as you're concerned, is the way that they're manufactured. So if you are trying to make that choice, I would go simply with price, because from a functionality standpoint for this system, there's going to be no difference. They also sell thin film solar panels. I would shy away from those. They tend to be less efficient, and for this system, the cost difference is going to be minimal. It's going to restrict the amount of usage, the amount of hours that you get charging power. So you may as well go with a polycrystalline or a monocrystalline. These panels normally come with what are referred to as MC4 connectors. These MC4 connectors, this is a male connector and this is the female connector. They're designed so that they interconnect out in the field like this, and they make a positive to a negative connection. I actually rigged up this adapter, and I terminated MC4 connectors on this end of it and just a standard cigarette lighter type connection on this side. But unless you're wanting to be able to reuse these panels, you could just simply cut off the MC4 connectors and then attach them to the positive and the negative wire on this connection point. It usually is a lot easier for people when they're doing this at home. The male connector, which is indicated with this little circle of red, is the positive, and the female connector is the negative. So when I hook these up with the male to the female and the male to the female here, I've actually made a connection, so when I do end up hooking it into my solar generator, our power input is just a female cigarette lighter. So if you are going to make this adapter, remember that the male plug from the panel is positive. The polarity of this plug is positive. So our jumper or an adapter, the female will have to be hooked up to the positive lead, and the male will have to be hooked up to the negative, because we're transitioning and making a jumper. So remember, even though the male is hooked up to the positive polarity on a panel, when we make this transition, we'll now be connecting to a female plug. So that one now has to be hooked up to the positive lead. And so to connect the solar panel to our solar generator, it's really now just as simple as plugging that in. So when this panel is set out into the sun, it will be charging the battery. So what determines what size solar panel you need? And the thing that's going to determine the size of the solar panel and also the size of your battery bank is going to be determined by your load. And when I say the word load, what I mean is anything that uses electricity is a load. So if you're plugging in a laptop computer, that would be a load. If you're plugging in a light, that would be a load. If you're plugging in a refrigerator because the utilities have gone down, that would be a load. So we have to do a load assessment, and this tool here, this little kilowatt meter, is a handy little tool for determining what is the load. And rather than get into some complication as to how you determine how much a specific appliance will draw, you can just plug this into the wall outlet using the standard plug, and then plug whatever you're wanting to test into here, and you'll see on the display how many watts it's using. And speaking of watts, let's go over here to the whiteboard. The first equation that we need, and there's not a lot of math in all of this, but the power equation is watts equals amps times volts. So this is a simple equation in electronics, but it's very powerful, not to use a pun. Watts is a measurement of power. So we've all heard of, like, there's a 60-watt light bulb, or you know, this particular television may draw 80 watts, something like that. Well, it is a combination of amps, which is the current that's flowing through that, and the volts, which is the pressure, the intensity. So if we use the water analogy, watts is the amount of water going through the pipe, and it is a function of how big is the pipe and how much pressure it's under. So it's just simply a relationship. Well, the one thing with this solar generator that we need to remember is everything in voltage must be consistent. So I'm going to be building a 12-volt solar generator. So the 12-volt solar generator, the solar panel must be 12 volts. So when you purchase a solar panel, make sure it is a 12 nominal volt solar panel. And the inverter, this is the second item that we're going to be dealing with. The inverter, its primary function is to take DC electricity that comes from the solar panel and turn it into AC electricity that all of our appliances use in the modern American household. Solar panels generate DC electricity, but all of our appliances use AC electricity, or I shouldn't say all, but pretty much all of the appliances that you would plug into that standard outlet that we looked at just a moment ago. So we need to somehow get the solar power to a usable form, and that's what an inverter does. When we're selecting the inverter, the criteria that we're worried about is it must be 12 volts, and it will say so right on the panel, on the unit itself. And we also are looking for how many watts of continuous power will it provide. And that will just tell us how much we can operate at any one time. So this particular inverter, this is a small one, and they're very inexpensive. I think this is $19, so it's not expensive at all. This is a 400-watt inverter. So that means it will service 400 watts of load at any one time. So for instance, if you're talking about 60-watt light bulbs, it would tell you that you could run 400 divided by 60, and that's going to test my math, but I think it's going to be about 6.5 light bulbs could be plugged in. If we plug in the 7th light bulb using this inverter, this thing's going to let out a little squeal, and it's going to tell you that it's reached its limitation. And something like this, I think, is designed just to shut down. Worst case scenario, you would burn it out. So you want to make sure that you don't overload this. It does have a brief period where it will handle up to 800 watts. That would be its surge, because some units, especially those that have motors, will surge in the initial couple of seconds that they're operating. So these inverters are designed for that. So the two selection criteria we need to worry about for our inverter is that it has the same nominal voltage as our solar panel, in this case 12 volts, and that the watts will meet the load demand that you're anticipating will be on the system. You can go with a very small 400 watt, Or in the larger example we'll show in a moment, I've got a 4,000 watt inverter. So we could run 10 times the load at any particular time. So far, as far as the equipment that we've selected a solar panel. Remember that that solar panel must be 12 volts. We've selected an inverter. Remember that inverter must also be 12 nominal volts, so the two have to match. The next piece of equipment we're going to look at is a charge controller. And a charge controller, once again, you got it, 12 nominal volts. So you'll be able to buy these. This little charge controller right here is only about $14, so it's not a very expensive. Whereas this charge controller right here does the same function, but it's about $300. This is something that would work great for a solar generator. This is really designed for a full house if you're doing charging a battery bank. These, from our perspective, are literally little magic black boxes. Either they work or they don't work. You're not going to be able to fix them. You're not going to be able to repair them. And they have ports where you will hook up the positive lead from the array, or in this case, a single solar panel, the negative lead from a single solar panel, the positive lead from the battery bank, and the negative lead from the battery bank. So the whole reason for a charge controller is to take the power from the panel and put it into the battery. And it controls that process. So it keeps the battery essentially from overcharging. If we had a solar panel hooked up to a battery and the battery was not being used and it continually received more and more power, these batteries, especially a lead acid battery, might overcharge and then it'll begin to boil and could actually damage the battery. So this controls that process and keeps it under, from undercharging and from overcharging. Oftentimes, too, there will be a connection for DC loads. So there's a positive and a negative connection point for DC loads. In this particular example, we're going to hook up the DC load directly to the battery. So it doesn't really matter. This is just a convenient connection point if you want to use it. And some examples of DC loads that you might do for something like this. In our case, we've got a meter that's going to tell you what the readout is on the battery. But you could be charging your cell phones. That would be a typical one for something like this because it charges using DC. The reason for this is when we do that transition from DC electricity to AC, you lose, in this case, about 10% of the power, transitioning it from DC to AC. So if we can go straight DC to DC, we don't have that loss. So oftentimes you will have a DC load charging port. Several times now I've mentioned DC electricity and AC electricity. So if we go back 100 years, Thomas Edison was really a proponent of DC electricity. And DC electricity is sort of how we might understand electricity from a layperson's point of view. So if we have the waveform, DC electricity looks just like this. If this is 12 volts and this is 0, and this is time, DC electricity follows like water through a pipe, just 12 volts all the way along. But then Nikola Tesla came along and he came up with this thing called alternating current, AC electricity. DC stands for direct current. And the alternating current, if we want to have, for instance, a 12 volt signal, the alternating current would go up to about 12 volts, then down to negative 12 volts, up, and this is what's referred to as a sine wave. And rather than water going through a pipe, this is actually the electrons are vibrating as they go through this wave structure. It's a much, much more complicated form of electricity, but it has advantages, which is why our system is typically AC. Now with this inverter, its whole reason for being is to take this flat line and convert it to a waveform. So in the early days, what it did was it started out And it starts at DC, and it would go positive 12 volts, and then it would reverse the polarity, which basically means turn the negative to positive and the positive to negative. And what that does is immediately changes the signal to negative 12 volts. And then it would go for another pit, and then it would reverse the polarity again, and it would go to positive 12 volts and negative. And this became known as a square wave inverter. And this was the early days of inverters. And you can see it begins to look like a sine wave, only very cumbersome. And this worked, but if you put up electronics on it, like radio or television, you got a lot of background noise, humming. Certain sensitive electronics simply would not work. So then they decided, well, we don't need to make this jump in all one bit. We can do it in increments. So they began the transition by stepping it down. And so this became a little closer to a waveform. And this became known as a modified square wave or a modified sine wave. And that's what you're probably going to be using, is a modified sine wave. When you go out to select an inverter, you'll see that in the descriptions it will often simply refer to it as modified or pure. Modified is a modified sine wave. Pure sine wave is one that, through the marvels of computer technology, takes that DC and gives you a pure rounded sine wave. And that's the ideal. But the reason why you'll probably be using a modified sine wave is just purely cost. Because a comparable sine wave inverter might cost $2,000, and a modified sine wave might only cost $300 or $400. So the fourth thing that you need to purchase, the fourth major component, is going to be a battery. And in this case, once again, guess what the voltage will be? 12 volts. 12 nominal volts for this system, and it says so right here. And it also says it's 35 amp hours. So if you're using a deep cycle lead acid battery, which is probably what you'll use in this solar generator, it will be rated in voltage, 12 volts, and amp hours. The more amp hours, the longer it will provide power to service the load. So remember our power equation. The power equation was watts equals amps, and we always designate amps as I for some reason. It's actually the French word for intensité de courant, but it's because the letter A was taken, but it is amps. Watts equals amps times volts, or watts equals amp hours. Now when we refer to amp hours, watt hours equals amp hours times volts. It may sound a little wonky, but there's an important distinction between watts and watt hours. Watts is a measurement of power, which is how much power it takes to instantaneously run something that uses electricity. And watt hours is a measurement of energy. And that's what we use, that's what we consume. So it's basically power over time. So when you buy electricity from the electric company, you're buying kilowatt hours, which is just 1,000 watt hours. So it is energy, which is power over time. So the battery is rated in amp hours. So watt hours equals amp hours times volts. We know that this is going to be 12 volts because our system is 12 volts. And we know this particular battery here is 35 amp hours. So how many watt hours? It would simply be 35 times 12, or 420 watt hours. Well, that's important to know because this is telling me I can run 420 watts for an hour, or I could run 42 watts for 10 hours. So now I just simply have to determine what is my load. And if I'm plugging in a small television, for instance, that runs and it takes 40 watts for it to operate, it's telling me I can run that for about 10 and a half hours before my battery goes dead. So size of the battery will determine how much load you can run for how long. And it simply comes back to that watts equals amps times volts equation. And in this case, it's modified to amp hours. Watt hours equals amp hours times volts. So these batteries, there are some safety issues to worry about with batteries. First off, this is an energy source. They can theoretically explode. These lead acid batteries give off a hydrogen gas, especially if they're overcharged. So one recommendation we're going to make when we go to build the case where this is going to be installed is to put some vents in the box so that if there is a gas buildup, this will vent out. Hydrogen occurs naturally in the environment. It's only when it's in concentration that it could be a problem. So we want to make sure this can vent out to the atmosphere so that you're not building up something that could technically spark and ignite. Another issue with this is it's very heavy. These batteries are heavy, and most injuries associated with batteries happen from somebody lifting them improperly, so they hurt their back, or they drop them, they land on their foot, or something like that. So a very practical concern is they're very heavy. Now, when you go to build your solar generator, after some experimentation, I found that I always want to design it so the battery sits in the center of the unit. My first design, I had the battery over on one side, and when I went to pick it up, the whole thing just sort of goes like that in your arm, and it's difficult to manage. So in the design that I have here, I've actually put in little bits of plywood, a little spacer bar down here, and the whole purpose of that is just simply to keep the battery weight centered in the case. So when you're carrying it around, it's not flopping all over the place. So depending on the kind of case that you decide to use, you may want to build that into your design criteria. Okay, so I put in some plywood here and here so the battery will center, and then a little spacer down here so that when we do place the battery, it rests in the middle without shifting around. Now, to review where we are at this point, the four major component pieces: solar panel, remember it's going to be polycrystalline or monocrystalline, 12 volts. The inverter, 12 volts, and the continuous watt rating is going to be based on how much load you want to service. So if you need something that can run 400 watts and only 400 watts, something like this will be fine. If you need a bigger system, for instance, this system over here, I put in a 3,000 watt inverter because this unit I wanted to use when the power goes out. I wanted enough power to run our well pump and to run our refrigerator and our freezer. So I needed more power because that little guy just simply wasn't enough to handle that load. So, and you'll see also there are bigger battery bank, so I can run it for longer. And it has the same charge controller because the charge controller is going to handle, really a little guy like that will handle whatever you need for a generator. But this unit that we're looking at right here will actually run a 20 amp circuit, which is a typical household room circuit, for as much as 2 or 3 days. So, so this is a nice emergency backup system. But unlike this, you're going to have a substantial investment in materials for a unit like this. This one is a nice starter. To continue our review, the third item that we needed to purchase is a charge controller. And remember, the component selection on this is, once again, that it must match the nominal voltage of the solar panels and of the battery. So we're going to go out and pick a 12 volt charge controller. And the fourth item, of course, is the battery. And it is 12 volts. The amp hours is going to be dependent upon how long we want to run the load. So when I'm looking at these components, the inverter controls how much load you can run. The battery controls how long you can run the load, and the panel controls how long it takes to recharge the battery. So those are the primary functions of each of these components. The battery must be deep cycle. You cannot use a car battery in one of these. And deep cycle batteries mean that the entire storage capacity of the battery is being utilized. With a car battery, you're only using about the top 5%. So you talk about cranking amps in a car battery, but a deep cycle battery, so a marine battery, like anything for a boat, or a golf cart battery, all of those will work. But when you're selecting the battery, just make sure it is a deep cycle battery. Once we've selected those components, now we have to wire them together. And this is where we can run into a little bit of trouble. You're going to want to select your wire, and wire comes in a number of sizes. This wire here, this size, would be referred to as 10 gauge, 10 AWG. This wire here, obviously much bigger, is 4 zeros or 4/0 wire. So the bigger the number, the smaller the wire. And the bigger the number, the less amps can be generated safely through that wire. So each wire has a limitation of the number of amps that can go through it. So when we go to hook up our system, what I will recommend is don't use any wire smaller than 10 gauge. This will make your life a little easier. These are easier to make your connections on. Small wire, it's difficult to crimp on the connectors. So don't use anything smaller than 10 gauge. When you purchase your inverter, it's going to come with some wire. Well, that wire has already been sized for that inverter. And you may as well use that wire for connecting the inverter to the battery. So that's very safe for you as well. If it doesn't, for instance, these larger inverters often don't come with their own wire. In those cases, you may have to do some calculations, but you'll always be safe if you just go with the 4/0. This is a kind of welder's wire, and you can use that. And you can get into the calculations of how we would figure that, but that's a little more advanced than what we need here. For the beginner, use the wire that came with the inverter, and you'll be safe. Okay, as they say, a picture is worth 1,000 words, so here's 1,000 words, right? We're going to draw a schematic of how this solar generator is put together, and this is not an electrical drawing, it's just a conceptual drawing. So I'm going to have a solar panel here. This is my solar panel. Don't grade me on my art. And remember, this is going to be 12 volts nominal. We're going to come in, and the first thing we want to connect to, we're going to go through this adapter here, but that will make a connection to the charge controller. So the rest of it is just connection points. From the panel to the charge controller, from the charge controller to the battery. This is 12 volts, this is 12 volts. So this is our connection so far. We're taking power from the panel, controlling it through a charge controller so that the battery doesn't overcharge, and then we're storing that in the battery. From the battery, we're going to go to the inverter. This is also 12 volts. What is it doing? It's taking the DC power from the battery and it's turning it into AC power that we can use in our appliances. From here, we're going to go out to our load. Now in this case, it's going to be just a single outlet that we can plug everything into. So now conceptually we're going DC power, 12 volts, being controlled, going to the battery, it will still be DC, going through the inverter, and it will now go to an AC outlet. Also from the battery, we're going to go to DC loads. And in this case, it could just be a USB for charging your phone or something of that nature. So there'll be 3 connection points here at the battery, from the charge controller to the inverter and then also to any DC loads that you may have. Somewhere in here, we would like to have a disconnect switch, some way to turn off the solar panel. And ideally, somewhere from here to here, we would like to have a disconnect from the battery. So each power source we would like to be able to turn off. So now we're beginning to make this system a little more complicated, But this is what's going to be in this box. This is also exactly how you would design a solar system for your home. No difference. This is a solar array in a box. No conceptual difference between this and running your entire home. The only difference is going to be the size of the components and, of course, the cost, the expense of it. This is conceptually what we're putting together. We have the solar panel or panels. If it turns out you need more than one, you can hook them up together. We're going to a charge controller. The charge controller is, as the name says, just something that controls the charge from the panels to the batteries. And then from the charge controller, we go to our batteries. That is where your energy is stored. From the battery, we're going to go to an inverter. The inverter takes the power from DC electricity and inverts it or converts it into AC. And then from the AC, we have an output, which in this case will just be an outlet that you can plug things in. Then we may also have DC sources, and typically that's going to be a USB port where you're going to charge mobile phones. Okay, so now that we know what the concepts are, let's look over here in the toolbox and see how they all get put together. Okay, so remember, we're going to go from the panel to the charge controller. We've made our connection here using this. This has an on-off switch, so we can actually make a disconnect. And then on the inside, we have the positive connection, which is here, and the negative connection, which is there. This connection is coming over to the charge controller. Then we've also made a connection, the positive lead to the battery and the negative lead to the battery. And then those wires come back over to this one, which would be the negative, and this one, which would be the positive, coming from our charge controller. So we could, at this point, hook those into the battery. So I'm going to take the black wire, typically signifies that it is negative. And the red wires I'm going to put aside for a moment because I don't want to hook them up, because I can begin to get maybe some sparking going on because this does have power in the battery. But ultimately it will be hooked in to the battery right here. Now from the battery, we've now hooked in our solar panel to the charge controller to the battery. The other item we need to hook in now is from the battery to the inverter. Well, we have the negative. The negative just simply connects on the back of the inverter right here. So we'll take our negative, connect it here. And we'll take our positive and connect it here. Now, this charge controller, what I like to do in my solar generators is protect the inverter with a fuse. So if we do, for some reason, hook up more load than this inverter can handle, this is just a simple automotive fuse, and it will blow. And that will protect everything in the unit. So I've just simply built that into the positive wire of this, the inverter connection between the inverter and the battery. Yeah. All right, so that goes in there. Then we'll set this in here. Now we could just simply plug in to the load directly here, but that would mean every time we wanted to use it, you'd have to open the lid and connect in. So I've wired a duplex outlet here and then the male plug here, and I simply plug that in to the inverter inside the case. So when it's time to use the power that's being generated, I can get that power from outside of the case. Now the positive is going to connect here. I'm going to hook the positive over here. I'm going to loosely connect this for a moment, just so wires aren't flying all over the place. I'm going to take the negative, connect it over to the negative terminal of the battery, and I'm going to connect the negative here. Loosely hook that up for a moment. So at this point the unit will work. We've connected the solar panel through a shutoff to the charge controller, from the charge controller to the battery, and from the battery to the inverter, and then from the inverter out here through this outlet to the load. But I want to add one more thing, because I found over the years that if I don't know what the state of charge is of the battery bank, the unit becomes very difficult to work with. So I'm going to add in a DC load, and because I don't want the meter to be on all the time, I'm going to put a switch in that. So once again, conceptually, let's see what we're doing. We've got a battery here, and let's say this is the positive, this is the negative, and then I've got my meter over here with my display, 12.5 volts, and it has a connection point that's positive and negative. So I'll want to run the negative wire from here to here, and I want to run the positive wire from here to here. That would be a typical circuit, but because I don't want it on all the time, I need to put my switch in, and in that case, the drawing of a switch would be right in here, and we only interrupt the positive leg of the circuit. So we will interrupt our positive wire by putting a switch in that wire. So we're going to run the negative from the battery to this load, which is the meter, and we're going to run the positive to one end of the switch, and then from the other end of the switch to the meter. Okay, so this is our meter right here, and I have the negative wire and the positive. I'm going to run the positive to my switch, which is mounted right above here, and it will terminate in there. Then I'm going to continue the positive by running it from here over to the positive lead of the battery. Now at this point, I'm going to be ready to tighten down all of these, because I think I've finally got everything connected to this battery terminal. Now one thing you want to make sure of when you're tightening these down is that the connection is firm, because loose connections will cause arcing from the battery, which is basically a little shock or a little spark that could generate out. You can use just a simple crescent wrench or some sort of wrench. When you do this, make sure that the metal wrench does not go from this terminal to that terminal, or you will get an arc that will ruin your day. So just be careful. This is electricity. You need to be cautious with it. If you don't wear glasses, you may want to consider wearing safety glasses when you're working here. So that the positive connection is made. Now I'll connect this to the negative terminal. And so now we just need to see, you'll notice the meter here is telling us the state of charge of the battery. It's right now saying it's 12.7 volts. You can use a multimeter of this sort if you want to double check that reading. It's a good idea. In this case, we're going to set it to DC voltage, 20 volts, and I'm going to test the terminals. Put it here and here, and it's showing me a 12.75. So the meter is accurately reflecting what the state of charge is of the unit. Now the next thing we want to check is it generating AC power? So I can put a little load in here. In this case, I've got a little light. I turn it on, it's not working. So number one in troubleshooting, what do you think's wrong? I probably haven't turned something on. So I'm going to turn on the inverter, and now the system is working. So this is showing you it is now generating AC power at the load. It's generating DC power here. Okay, right now this generator is operating, And if you listen to the sound of the beautiful birds chirping in the trees, this is as much noise as it's going to make as it's running your appliances. So you can take this into your home. You don't have to worry like a gas-powered or diesel-powered generator where it's spitting out fumes. They can be quite dangerous. They can be quite loud. You certainly wouldn't want to operate one in your living room to watch television or to run your refrigerator. So this will not make any noise, perfectly silent. And when you shut the case, you can just carry it around wherever you wish. Handy little tool to use when the power goes out, or when if you've got a remote application. We've used some of the larger ones when we've done construction out in a remote field to run chop saws, to repower your drills, to recharge the batteries of your tools. And they're quite nice because if you've ever worked in a remote location, you're trying to get back to nature and all of a sudden it's a generator that's just generating all this noise and fumes, and it kind of spoils the whole zen of the project. Okay, the actual design and creation of these solar generators is pretty basic. Once again, like to keep reviewing, you're going from solar panels to a charge controller, from a charge controller to a battery bank, from a battery bank to an inverter, from the inverter to your load, and then if you have DC loads, from the battery bank to your DC loads. That's the concept. Now the big question is, okay, how big of a solar panel do I need? How big of a battery bank do I need? How big of an inverter do I need? Those are going to be the questions that you have to answer, and that will be 100% dependent upon your load. So let's use the example of a small office. Okay, I do my load assessment, and it turns out when I look at my laptop uses about 45 watts of power. That's an instantaneous measurement of how much power that laptop uses. Then I have a small little desktop lamp. Let's say that uses about 10 watts. It's a little LED lamp. I've got a modem, and the modem is connected to the internet, so that uses about 5 watts of power. And then let's say I want to use my printer, and my printer uses about 30 watts of power. And now it's going to be a matter of what else do you need to run your home office? At this point, I've got a laptop, a light, a modem, a printer, maybe a coffee warmer. I don't know about that. Let's just say this is our home office, and we want to make sure that this runs. Well, we add up all of the watts that are going to be used at any one time, and we find out it is 90 watts. Well, this is our maximum power draw. This is the amount of power we might use at any particular second. This is going to determine the size of our inverter. So I look at my inverter. Well, the inverter that we used in our example was 400 watts. More than enough power to service this load. I need at least 100 watts to service this. I've got a 400 watt inverter. So that part is now solved. So now the next question is, how long do I want to operate this? Well, let's say I want a full business day of backup power. So 8 hours, of course, your business day may be 12, sorry for you. So 8 hours, so 90 watts times 8 hours is going to be 720 watt hours. Watts times hours, 720 watt hours. Well, in our example, the battery was 35 amp hours. So how long? Well, we determined that this is watt hours, and we know watts equals amps times volts. So I would divide this by 12 volts, and that's going to give me 72 divided by 12. Now the math starts to get outside of my realm of comfort, but let's say it's going to be, what, 60? 60 amps. So 60 amp hours is required to operate for 720 watt hours. So this battery would not service my load for 8 hours. I would need a 60 amp hour battery to service my load for 8 hours. So if I do select this particular battery, I have to then make my calculations, and I'll find out that rather than 8 hours, I can go maybe 4.5 hours servicing this load. There are a couple of complications to this. One is you can never use 100% of the power that's in a battery. So we can only go to about 90% of this, so it will be somewhat less. But the other complication is you could be using this while the solar panel is plugged in, at which point it will be replacing some of the power as it's using it. So it depends on how much sunlight is available at that particular moment as to how long this will actually run. But you can get a rough idea just using this simple math. Now, when it comes to determining the size of the panel, that's going to tell us how quickly will it recharge the battery. In a typical location in America, we get about 4 hours each day of pure sunlight, or what's referred to as insolation. Doesn't mean the sun only shines for 4 hours and it's dark for 20 hours. It just means that pure sunlight, no clouds, no shading, direct sun, when we average everything up, it's going to be about 4 hours of pure sunlight. So we can assume we have about 4 hours of insolation at a particular site. And then we need to know what is the watts of the panel. This panel that I've been showing in this demonstration is a 30-watt panel. That's its rating. So if I were to put it outside on a typical day, I would get 30 watts times 4 hours. I would get about 120 watt hours of power each day. So in this example, if I needed 720 watt hours for 8 hours, if I used this particular solar panel, it would take me somewhere in the neighborhood of 6 days of that panel sitting out in the sun to recharge my 1 day of usage. So if I wanted this to recharge each day what I used each day, I would need a panel that is not 30 watts, but I would need probably 30 times 6 or 180 watt panel, which would be a significantly larger panel. But if it's simply an emergency tool that's here to handle emergency backup in case the power goes out, it may be very common that you'll have 6 days of power connection for, hopefully it's common, you'll have 6 days where the grid is working for every 1 day it goes down. So you'll have 6 days to recover with your solar generator. So this gives you a taste of some of the math that's involved when we go to size our battery bank, and when we go to size our inverter, and when we go to size our solar panels. The solar generator is a good project. We've only gone over it in just in an overview. I've got a book here that talks about all of the details about wire sizing, battery bank sizing, array sizing, how to do those calculations in fuller detail. Also where to source all of the bits. You can buy the toolbox almost anywhere. You can buy most of the components at your local battery store or at online, Amazon.com. All of these things are available. Inexpensive. The entire unit will only cost about $230 or so. And if you get some things on sale, even cheaper. It's a good school project if you're wanting to do something like that as a demonstration. And when it's over, you actually have a useful tool that you can use in your everyday life at home or at work or in school to perform almost any function. It's a great demonstration of what solar is all about and how it works.